Hi guys, welcome to today's lesson. So today we are going to focus on triangles and quadrilateral riders, right? So riders are just questions that we are going to do that need you to apply some properties of triangles and some properties of quadrilaterals based on what you have at the time. So let's just jump right into it. So remember, when you talk about riders, there's a few things that you need to make sure that you go through properly. So firstly, you need to make sure that you read through the facts part. This will be the statement that I give you. So in the diagram below, ABC is a triangle with. And then because of those widths that I would have added, you will then need to mark them on the sketch to make sure that you are able to see them visually. And then you also mark your implicit facts. This will be things that are not really told, but you can apply them based on what is told to you. Then you read through the asked part. So this is where you then go to understand what the question wants of you. You devise a plan of action. This plan of action is very important because I promise you, most of you guys just go straight to trying to say, oh, let me try solve the problem. But if you don't have a plan of where you are going to start, you're going to include a lot of unnecessary things, especially in geometry. And then evaluate, plan, and restart, right? So that's what you then need to be able to do. Evaluating plan means you do execute it and check whether your solution does make sense. If not, you can always go back. There's now ways to check if your answer is even correct or not. Now, when you talk about tools for solving triangles, riders, so this is, you need to make sure that you know the properties of triangles. When I talk about properties, you know, we have like a scalene triangle, what are the properties? An isosceles triangle, what are the properties? An equilateral triangle, what are the properties? Even a right-angled triangle, what are the properties? So that's what I mean when I talk about the properties. And outside this, are there any theorems that we need to know that have to do with triangles? Also, you need to understand how to show that the triangles are identical. Remember, identical will be congruency. So this will be congruency. And then similar will be similarity, right? Because triangles can be similar or they can be identical. There's a difference. The identical means angles are equal, sides are equal. Similar would mean angles are equal, but sides are in proportion. Now, the types of triangles, as I said, we have a scalene, an isosceles, and an equilateral triangle. And you know the different properties that we have here. This, no sides are equal. No sides are equal, and also no angles are equal, right? With an isosceles triangle, we know that two sides are equal. Two sides equal, and two angles equal. Then with an equilateral will be three sides equal, and also three angles equal, right? So those are the properties of these types of triangles. Now we're going to look at what exactly how can we classify this according to the lengths of sides, right? So if I talk about sides, it means that side and that side are equal, that side and that side and that side are equal. So three of them makes this to be the equilateral, and makes this one to be the isosceles, makes this one to be a scalene, because none of the sides are equal. If we look at this from the size of their angles, then we can always say that this angle is equal to that angle there, which would therefore mean that this is a right-angled triangle, right? This will be an acute-angled triangle, and this will also be an acute-angled triangle, which is more of your scalene. And that one, we can always try classify it based on those lengths that we have there. Now, the terminology that you need to make sure you understand under the concept of riders is, what is a theorem, right? So this will be a statement that has some proof to it, right? So if I say line AB is equals to line BC because they are being bisected by a certain line, that will be a theorem, right? And then if I want to talk about the converse of a theorem, I would say if a line bisects a longer line at point B, it will cut the line such that AB is equals to BC. So now we're starting with the bisection. But let's actually look at this from a more realistic way, right? So the theorems that we have, which I'm going to look at, also the converses of them, is the sum of interior angles of a triangle is equal to 180 degrees. Now, the short way of writing this, which you need to be able to know, will be to sum of angles in triangle, right? That's all you need to do. As soon as you have sum of angles in a triangle, a person would know that they need to equal to 180 degrees. So that's how you then write that down. Also, we have what we call the exterior angle is equal to the sum of the opposite interior angles. Now, this has to do only with a triangle. And how to actually see this will be when we have one side that is produced, which we're going to talk about as well. Then this will be equals to, if that was x and y, it will be x plus y. And the short way of writing this as well will be exterior angle of a triangle. And you leave it there. You don't need to then continue and say is equal to the sum of the interior opposite angles. Another theorem that we have of a triangle is to say in a triangle where two sides are equal, the base angles are equal. Now with this one, I want you guys to then think about how can I make a converse of this particular theorem? So I know that if my triangle has two equal sides, it's an isosceles triangle, then the base angles are also going to be equal. It means if I wanted to look at it from a converse perspective, I will then say if the base angles are equal, then the sides are going to be equal, which will then make it an isosceles triangle again. So that's how the concept of a converse comes in. Two sides are equal, the conclusion, two angles are equal, right? And then the converse will be if the two angles are equal, the conclusion will be the sides opposite. Those angles will also be equal. And then it still is an isosceles triangle. So let's look at it from the writing itself, how you're going to write the converse. Right, so the converse will be in a triangle where the base angles are equal, the sides opposite the base angles will be equal. So what do I mean with this? If I have something of this nature, this angle and that angle are equal to each other, it would therefore mean that the side opposite, which is this side here, and the side opposite, which will be this side there, will be equal to each other because they are opposite those angles. So that's how you look at this particular concept. Another theorem that we can try and talk about will be for an equilateral triangle, which says in a triangle where three sides are equal, the three interior angles are also equal to each other. Now, I'm sure you are already thinking of the converse, right? That if the three interior angles are equal, then the triangle will have all the three sides also equal. Right, so that's what we are going to say. In a triangle where three angles are equal, the three sides will also be equal. Now, in a right-angled triangle, here we are talking about the theorem of Pythagoras, right, which you are very familiar with. The square of the hypotenuse side is equal to the sum of the squares of the other two sides, right? And you're going to classify this in terms of lengths and see what it says. The converse of this will be if in a triangle I have the square of the hypotenuse being equal to the sum of the squares of the other two sides, then the angle that is opposite the hypotenuse side will be 90 degrees. As you all know that the hypotenuse side is always the one that is opposite the 90 degrees, right? And the short way of writing hypotenuse is normally HYP, right? So if I say this squared is the same as this side squared plus this side squared, then I will know that this is a 90-degree angle. Let me repeat. If I say this squared is the same as this one here squared plus that one squared, then the angle that is here will be a 90-degree angle because this will be adhering to the theorem of Pythagoras, which is the converse we are talking about. Now, with congruent triangles, remember I spoke about we can use the properties to talk about whether they are identical or not, right? If they are identical, it means the three equal sides need to be seen, and also the three equal angles need to be seen. But you don't need to prove both equal sides and equal angles. You can choose to show three things equal, not all six. So you don't need to show all of them to be equal to each other. What do I mean? If I prove by congruency, I will have a right angle in both the triangles. I will have a hypotenuse. I will also have a side. We call this RHS, right? I can prove this as one of the ways to talk about congruency. We also have what we call a side and an included angle and a side, right? And I can also use this to prove congruence. Not that I must prove it with the first one. No, I can use either one of the first two. Then the third one will be side, side, side. Remember, all three sides are equal. Then I can try and use this one as the third option. Not that I'm using all of them. And then the last one will be side, angle, side, which you can use either one of the four conditions of congruence. And then remember as well, we also have the similarity. And the similarity that we need to prove, we normally prove it using equiangular, right? Angle, 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 meaning you must prove all three angles are equal, but you just need to prove the first two, and then the third one will be equal as a result of the first two. So that's what you guys need to please make sure that you understand about the properties of triangles, right? And all of this is what you guys already know. But now, when we come back from the ad break, I want us to then apply all of this that we've spoken about in terms of the riders to then solve these questions and see how do we visually see the properties and how can you apply them in order to solve the questions that are presented to us. Please stay tuned. I'll be back just now. Hi guys, welcome back from the ad break. So we are still looking at solving some riders that have to do with triangles, right? We looked at the properties of triangles first, all the triangles that we have in mathematics, and then we looked at how we can talk about the theorems and their converses. Now we're going to need to apply all of these in terms of solving some riders. But first, let's just quickly go through the map that we need to go through in order to solve the riders, because now we need to apply it, right? So, remember, what did we say? We said, firstly, you must make sure that you read through the facts part, right? The facts part will be maybe the type of triangle that they told you, right? They told you the type of triangle, or they are telling you about equal angles, or they are telling you about equal sides, right? So those are the facts that you are going to try. And then turn those facts into part of the sketch that we have, right? So if they said in this triangle and in that triangle there are two equal angles, you will then do this and say that and that are equal, right? You are told. And then you go to the implicit facts. So implicit facts will be when they just use terms like this is parallel to that. You know that they are not simply telling you what the properties of parallel lines are, but because you know that they are parallel, then you can think about your corresponding angles, you can think about your co-interior, you can also think about your alternate angles. So that's just an example of what it means to look at an implicit fact. Also, you then continue, after you do all of these things that we've done, the first three things, and I promise you, they're actually the most important things in this particular type of mathematics, which is geometry. And then you go to reading through the asked part. So this is to read the question that is given to you, right? The question that they gave you. What do they want you to do? Right? You will look at things like RTP. What is required to be proven, right? What is required of you? What do they want you to try and show? Then from that, you will then say, okay, if they want me to prove angles are equal, then it means I must start by linking angle 1 with maybe angle C, right? Because at the end, I know that angle C is linked to angle F, which is what I'm trying to talk about. So do you understand? My thinking process will be that. Now I'm saying, all right, so I don't only take all the angles because there are a lot of angles. I'm only going to try and link A, C, and F because they are the ones that I want. So that is my plan of action. Then you go to apply the plan that you have and you always restart again, provided that maybe you think you did not get it right or something that might have thrown you off. Now, the terminology that they use under this concept of riders is what you call the bisect, right? The word to bisect means to cut in half, right? This is to cut in half. Right? So if a line is bisected, it means that AB being bisected here, it will make it to be AM, let's call this M, is equals to MB, right? That's what bisected means. Even with an angle, if I say this angle here is bisected, it will be divided into two angles which are going to be equal to each other. So that's what bisect really means. But now let's see how we can apply all of this in terms of the riders themselves. They say BCD is a triangle, all right? So now I know this is a triangle that I'm going to focus on, with BD produced, the very most important thing that you can ever find in mathematics, especially in geometry. This simply just means extended, right? So the line is extended. Now, because of that, the implication is I can talk about the exterior angle of a triangle. Why? Because I know that one side is produced or is extended, right, to the point A. So in simple terms, I can try and talk about angle A being, angle D2 being equal to D plus C there, right, because it will be the interior angle. Now, CE is a bisector of BCD. So BCD, which means that angle and that angle are equal to each other, right? I'm going to show you a proper diagram just in the next slide. Then this also meets AB in E. So that simply just tells us that it is a straight line that is intersecting another line. So we are required to do that. But before we even entertain the question, let's actually apply what they've told us in the diagram properly. We know that C1 is equals to C2. That's a given to us. Now, what else do we know about the angles in these triangles, right? So we need to try and apply other properties that we know. So I know that this will be equals to angle B plus angle C1. right? You see, so this will be an exterior angle of a triangle, and then this angle will actually be angle B plus the whole of C now, right? So it's like 2C1, and that's how you can think about the other properties of angles in this shape. So let's try and prove that D2 plus B, right? So D2, which is this, plus B is equals to 2E2, right? All right, so what do I know about E2? My plan of action is I must try and use E2 because I know that E2 is equals to C1 plus angle B, right? And then I want to make B the subject of the formula, right? But I also know that D2 is equals to 2C1 plus B, right? So you can now see what is happening here, right? What this simply means is if I want to make E2 the subject of the formula, which is at this point, I will then say E1, all right. So I will then say, let me just substitute the B there. I will have B is equals to E2 minus C1, right? And therefore, D2 will be equals to 2C1 plus the angle B there we said is E2 minus C1, right? And then you can see 2 minus C1 will then be what? 2C1 minus C1 will be C1, right? So this will be D2 is equals to C1 plus E2, right? But now I want to make sure that I have twice of this particular E2 here. If I wanted to get twice the E2, I will also use this angle here because this triangle will be an isosceles triangle that I have. So that's what you will therefore need to do. So at the end here, I will need you guys to please use that triangle to try and talk about D2 being that, because I want to just show you one more question and then we can then leave it at that. So when we talk about the terminology respectively, it simply means that is what you are given in the diagram. So here we are told that these are the bisectors of FGH and FHG of triangle FGH, right? Which is respectively. So simply means that this bisects that and this bisects that, right? So that is that one and that is that one. All right, so to apply this, we then know that we are given G1 to be equal to G2. That's because of the bisector. And then as a result, I1 is also equal to those two because of alternate angles, right? And on the other side, I know that H2 and H1 are equal, which automatically will be equal to I3 because of alternate angles. So what do we recognize? That becomes an isosceles triangle, and that becomes an isosceles triangle. Now, to solve what they want us to do, the very first thing we know is JK, I mean, is equals to JI plus IK, right? Is this part plus that part. But we know that this is equals to that and this is equals to that. So as a result, I will then say JK is equals to JG plus KH, not KG. Right, so KH. And you can even start by first mentioning that JI is equals to JG and then IK is equals to KH. And that's how you can then solve what the question is asking of us. All right, guys, we've come to the end of our segment for now, which we are going to take a quick ad break because when you come back, we have some more work that we are going to do. But for now, please stay tuned. I'll be back. Hi guys, welcome back from the ad break. So we are still looking at some riders that have to do with triangles and quadrilaterals. So now we're going to focus mainly on quadrilaterals and try and apply those properties that we know about those quadrilaterals. So let's just go to the very first question that we need to look at. But first, we're going to look at some properties that we need to remind ourselves of. So remember, the terminology that we use for the special quadrilaterals is what we call opposite. When I'm saying opposite, we know if it's sides, then that side and that side are opposite, and that side and that side are opposite, right? Even these angles here are opposite. And let me use a different color for that one so that it's not a lot of things that don't make that much sense. And that one are opposite, those two angles, and those two angles are also opposite, right? We also have what we call a diagonal, which is also the red parts that I have on my diagram, that and that. Lastly, we have a produced, which is very important, and I had already explained. If I say something is produced, I mean it is extended, right? That's where it is. You can see the extended part of Ln. So Ln will be produced to Nm. That's how they would say it if they want you to use that particular concept. Then you can talk about an exterior angle of a shape, right? Based on what shape that is. Now, if we have a parallelogram, just to remind ourselves of what a parallelogram is all about, we know that both pairs of opposite sides are parallel, right? And we also know that they are not only parallel, they are also equal to each other. We know that both pairs of opposite angles are equal, and then the diagonals bisect each other. Remember, bisect will mean cut in half, right? This is to cut in half. Now, let's put this into a more needy way of doing it, right? What is all of this all about, this parallelogram? Let's try and see how can I now use this in a diagram. So they say LMOP, LMOP is a parallelogram. Now I need to immediately switch on my brain on what are the properties of a parallelogram, right? And then N is a point on MO such that Lm is equals to Ln. And then we are required to prove that, right? But for now, we don't want to focus much on the proving, right? Since this is a parallelogram, we know there's parallelness there, right? There's parallelness there. We know that there is equality here, and then there is equality there, right? But what we are told is that this is equals to this. So as a result, there's three lines. 1, 2, 3 that are equal, right? That might come in handy somewhere. But we will see whether we do need that or not. And then since this is equals to that, and we are told it means this angle here will be equal to that angle there, right? That's because of the fact that the triangle will be an isosceles triangle, and then it will automatically be that one because of alternate angles. So now I have three angles that I have that are equal to each other. But also, just to add one more angle, that angle is also equals to the opposite angle, which is M. So I have 4. Now my list is going higher and higher. But let's see how we're going to apply this, right? So we know that this is also a two-liner there because it is opposite the M, and then we also know that it is also equals to that. But what exactly do they want me to do? Hey, I've already proved what they want without even proving it. This is nice. But anyways, let's write the mathematics of it, right? So we know that P is equals to M, and this will be properties of a palm, right? And then actually I want us to maybe say opposite angles of a palm, right? Instead of properties, because which property are you talking about? So let's rather use opposite angles of a palm, opposite angles of a palm. But now I also know that the angle M is equals to angle N1. And this is because it's angles opposite equal sides, right? And then from there, I know that N1 is equals to L2, and my reason for this will be alternate angles because LP is parallel to MO. As a result, I know that P is equals to L2, right? And you know that L2 is this one here, NLP, right? And you don't need a reason for that, but you can always just say P is therefore equals to NLP, not angle at N, right? You can always go back and write it the way the question wanted you to do it, which is NLP. But NLP is this angle here, NLP, which is just L2. Now, in the diagram, ABCD is a parallelogram. All right, parallelogram, there's some interesting things. There's a lot of nice things about a parallelogram. With these diagonals intersecting at E, so what does that tell me? It tells me that this will be equals to that, right? I know that. And then also the diagonals of a parallelogram, DECF, intersect at G, right? They intersect at G, which is at that point. The diagonals of parallelogram FGCH intersect at that. So now I have actually 3 parallelograms here, and I'm going to highlight them with different colors, right? So the first one will be this one here. The second one will be this one here. And then the third one will actually be, I'll use the same color, maybe like this, right? It will be this one here. See, so now I have 3 parallelograms that I have. One that is a wobble, one that is just a red line, and one that is a blue line. So there's a lot of nice things that I can say in there. But what I just want to prove is to talk about DB being 4 times KC. Let's try and look at that. Right, so remember this is equals to that, this is equals to that, and we also know that, where's the other parallelogram? This one is equals to that, let's make it an X, and then this one is equals to that one there, right? We can do equality with a lot of things here, but for now, they don't really matter much because we are going to use KC, right? So in color, look at what KC is, right? KC is half of FC, right? So KC is half of FC. But also I know that FC is equals to DE, right? So therefore it means KC is equals to half of DE. But I know also that DE is equals to half of BD because it is a diagonal. So as a result, that will therefore mean that KC is equals to 1 over 2 into 1 over 2 BD. And then if I multiply them, I will get KC is equals to 1 over 4 BD, and then if I want to simplify this further in order to write it the way they want it, I will then have BD is equals to 4KC, and that's how I will then need to prove this, right? So please make sure you're always going to write your reasons, right? The reason for FC being equal to DE will be opposite sides of a palm, opposite sides of a palm. The reason why KC is equals to that is because we just substituted, right? Even here it will be diagonals of a palm bisect, diagonals of palm bisect. And then from there, you can always try to find reasons with the others. It's all about the properties of a palm. It's either because of the diagonals or because of the opposite sides of a palm. That's what I was trying to use here. So that's how you then will prove what they wanted us to prove. Really, guys, I hope this is making so much sense to you, because I promise you, parallelograms are a very big part of your mathematics at this particular level in terms of your Euclidean geometry. So you need to make sure that you grasp every concept that is there. But for now, I want us to take a quick ad break. When we come back, we're going to look at some more quadrilaterals and try to prove some riders that have to do with them. Please stay tuned. I'll be back just now. Hi guys, welcome back from the ad break. So now we've come to the last segment of our show, where we are still looking at some quadrilaterals riders, right? To try and solve some questions based on now either maybe a rectangle or a rhombus. But let's see what quadrilateral you have next. So I want you to please stay tuned with me as we are doing these last questions that we have. So remember, guys, this map of mine is very important. Read through the facts, mark on the sketch, go to the implicit. So because it's a parallelogram, what else do you know that is not told? Read through what they want you to do, a plan of action, evaluate it, and always restart. So please just remember to always do these things. And it is really in this order, guys. I promise you, it starts here. There is nowhere where it starts other than you reading the statement. Now, if we have a rhombus, right, so it means our quadrilateral now is a rhombus, which is a very interesting one. What do we know about it? All the properties of a parallelogram are very true when it comes to a rhombus. Now, what makes it different from a parallelogram is that the sides are equal, all of them. The diagonals bisect at 90 degrees, and then the diagonals bisect the angles as well. So these three things are what makes it a very different parallelogram. So if I wanted you to then prove that something is a rhombus, it means you would try and uphold the properties of a parallelogram, but that will not be sufficient, because then you would only have proven it to be a parallelogram. To make it a rhombus, then you must add one of these three properties in order for it to make sense. Now, here they say RSTU is a rhombus with RU produced to V. I'm stopping there. I don't even want to continue. So what do I know? I know that this angle here will be equal to that angle there, right? That's because it's a diagonal, which will be equal to that angle, which will be equal to that angle, right? And then because of that, it would mean that this angle here will be equals to T2 plus R2, right? Because it's an exterior angle of a triangle. And then you can always talk about the other angles based on that. But for now, let's just see how we can use that, what I've just mentioned now. So they want us to prove that U1 is equals to 2T1. So that's how the diagram will look because of my nice properties that I know of a rhombus, right? By the way, we call it a rhombi and triangles, right? Because if we're trying to look at it from a point of how many angles are there, which is a plural, right? Now, if we want to use the deductive reasoning for this, I want to prove that U1 is equals to 2T1, right? Which is the same as T1 is this angle there, right? Which is the same as 2R, what is this? R2, which is also the same as that one there, 2T2. So I must make sure that I understand what I'm trying to do here. So I'm going to first say U2 is equals to T2 plus R2. So I will try apply this and see whether it will work, right? Exterior angle of a triangle. And then from there, let me actually write my reasons properly, guys, so that you know that you are required to write them properly. Exterior angle of a triangle. And then from there, what do I know? I know that T2 is the same as, rather I will say R2 is the same as T2, which is the same as T1, not R, T1, right? This is the same as T1, and this will be because there's alternate angles. That is because ST is parallel to RU, right? Then from there, what do I know? I know that it means U2 will actually be the same as, if I want to add these angles, it will be T1 there plus T1 there, right? Which is the same as U2 is equals to 2T1, right? Then from now, I want to then relate this to U1, right? Because I'm only talking about U2, right? So there's what we call, if I want to relate it to U1 here, there's what we call an exterior angle of a cyclic quad, which will be equals to that angle that I have there, right? So I know that U2 is equals to also S, and this is because exterior angle of a cyclic quad, right? Or an exterior angle of a quadrilateral, and then as a result, it means U1 will be equals to S, which will be equals to 2T1, right? U1 and S are equal because these are opposite angles of a rhombus. And that's how you can then prove what they want us to prove. Now, another question that we have here. So this one, guys, I promise you, you need to make sure that you are paying attention and your algebra skills are on point. So here it says, in the quadrilateral ABCD, diagonals AC and BD bisect at O, right? So AC and BD, making this to be equals to that, making this to be equals to that. Immediately I know that it makes this a parallelogram, right? And then what do I now want to do? I want to prove that this is a rhombus. So before that, let's just add a few of the things that we know. So we know that this will be the same as 2xy, and that will be 2xy, because it is bisected, right? We were told that this is bisected. And then this one and that one, I want to know what it is. So this will be not 2, just x. This one will be x squared minus y squared, and then this will also be x squared minus y squared, right? And then I can then try use all of these nice things that I have here. So remember, for me to prove that this is a rhombus, already I know it is a parallelogram because the diagonals bisect. I must just prove that this is 90 degrees. So this is my required to prove, which is RTP, right? I must prove that this is 90 degrees, right? Which is BOC is equals to 90 degrees. If I can prove this, Guys, I would really would have done what they wanted me to do, which is just to prove that this is a bus. Now let's quickly, again, remember I said you must add either all the sides are equal, diagonals bisect at 90, or the diagonals bisect the angles. But with the angles, it will be a bit difficult because then we will need to measure, and remember, geometry we don't measure, we just apply the theorems and the properties. Now I'm going to use this triangle here, right? In this triangle, if I find that this squared is equals to this squared plus that squared, then I would have proven that this is a rhombus. So let's quickly try and do that. So I will first say the left-hand side, right? Or not even the left-hand side. Okay, let me write it as the left-hand side, right? So I will say the left-hand side will be, let's take it as the hypotenuse side, x squared plus y squared, right? Now I must square this. So to square this, it will be x to the 4 plus 2x squared y squared, and then plus y to the 4, right? And that's what I will have there. So it will be those two times together times 2, yes. So this is what I will have on the left-hand side if I call it my left-hand side. And by the way, my left-hand side is BC squared. Now I want to know what is BO squared plus also OC squared, which will be equals to, let's look at BO. BO, we know that this is x minus y squared, and then it will be plus, I square this, 2xy squared. Okay, and therefore, this will then be equals to, if I simplify this, it will be x to the 4 minus 2x squared y squared plus y to the 4, and then plus 4x squared y squared. And then as a result, this will be equals to x to the 4 plus 2x squared y squared. Why? Because these are like terms. This one here and that one there are like terms. And then lastly, it will be plus y to the 4. Hey, guys, look at this. How beautiful is this? This is the same as that I have there. So as a result, you will then claim that, therefore, BC squared is equals to OB squared plus OC squared, which means that BOC is 90 degrees, then ABCD is a rhombus, right? And the reason for that will be the diagonals bisect at 90. Diagonals bisect at 90. Bisect at 90 degrees. And that's what makes it a rhombus in that particular regard. So I hope that clarifies a lot of things, guys. Remember, you always need to make sure that you understand what is given, what is required of you, and what is it that your plan is going to be, and what is it that is hidden from what is given. Because the times what they give you is not what you're going to apply. You're going to apply the hidden information about what is given. Guys, we've come to the end of our lesson. I hope you've enjoyed as much as I have as well. But remember, every good thing needs to come to an end. Until next time, please look after yourselves and remember, mathematics is food for the soul.